Today, we're going to cover one of the powerful tools in mathematics. It's called mathematical induction, and I'm going to be doing it in three parts. Today, we do part one. If Pn is a propositional function, so logical function, where n is a positive integer, the question is, if we know that Pn is true for n equals 1, 2, 3, up to, say, 1,000, can we then be sure that Pn is going to be true for all values of n? I'm going to start with this simple example. I'm comparing, excuse me, 10n squared with 2 to the power n. And when n is 1, 10n squared will be 10, and 2 to the power n will be 2, and this one is like 5 times larger than this. When n is 2, 10n squared is 40, which is about, it's 10 times 4. 3, you get 90, you get 8 here, 4, 160, 16, 10 times more. So 10, 4 squared is greater than 2 to the power 4. 5, 6, 7, 8, 9, getting closer, 10, very close here, 11, the inequality now changes direction. Now this term is less than this. 12, less than this. If you go up to 20, you see this one is 4,000, but this one here is 1,048,576. You see how this one is much smaller than this. Now, actually, if you replace this by, say, 100n squared, you have to go a little bit more than 12 for this inequality to change direction. Now, this example, 1 is equal to 1, 1 plus 3 is equal to 4, 1 plus 3 plus 5 is equal to 9, 1 plus 3 plus 5 plus 7 is equal to 16, and then you add 9 here equal to 25. So what I'm doing here, I'm adding the first few odd integers. And I'm getting these numbers 1, 4, 9, 16, 25. So I noticed that these numbers are perfect squares. So like this one here is 5 squared. This one here is 4 squared. And this one here is 3 squared. 2 squared. 1 squared. So there is some kind of patterns happening here. And now I need to see how this 5 square is related to this. So technically you have 5 terms here. You have 4 terms here, so you get 4 square. You have 3 terms here, you get 3 square. Now also you can notice that this 7 is 2 times 4 minus 1. This 9 here is 2 times the same 5 here, 10 minus 1. This one here, 5, is 2 times 3 minus 1. So now we write this again. 1 is equal to 1 square, 2 squares, 3 squared, 4 squared, 5 squared. Now, can we, seeing this taking place for these few steps, can we then say that for any n, the sum of the first n positive odd integers is n squared? That's the question that we need to answer. Here's another example. 1 is equal to 1. Now 1 plus 2 is equal to 3. 1 plus 2 plus 3 is equal to 6. Add 4 equal 10. Add 5 equal 15. Now this one is kind of a little bit difficult to tie or relate this to 4, or this to 5, or this to 3. But it's not really too difficult to notice that if I take this 2 times 3, 6 divided by 2 is 3. So here, 2 times 3 divided by 2 will give you that 3. If I take this 3 here, 3 times 4, 12. Divided by 2, I get the 6. If I take this 4 here, 4 times 5 divided by 2, I get the 10. If I take this, it'll be 5 times 6, 30, divided by 2 will give you the 15. So I see the pattern now. So I can put y, 1 is equal 1, that 1 plus 1, 2. 1 times 2, 2 divided by 2 is 1. This, you take the 2 and you add 1 to it, 3. 2 times 3, 6 divided by 2 is 3. You take the 3 here. 3 plus 1 is 4. 3 times 4, 12 divided by 2 is 6. And you see how that's happening. Now, again, I'm going to write down here, can I be sure, just running this for a few values of n, is this going to be the case for all values of n? Can I prove that 1 plus 2 plus 3 up to n is equal to n plus 1 over 2 for all values of n? This is the question. We'll come back to that. Now, what is the principle of mathematical induction? You need to prove for any n greater or equal than 1, Pn is true. What you do, you prove two things. Basis step, and sometimes it's called base step, and inductive step. Base step, you prove P1 to be true, and then you prove Pn implies Pn plus 1 is true. So now what happened, you see now P1 is true, and since P1 implies P2 is true, now P2 becomes true. Now P2 is true, and P2 implies P3 is true, then P3 is true. And you put P3 here, P3 is true, P3 implies P4 is true, then P4 is true, and so on and so forth. Now I'm going to apply this mathematical induction to this example that we just mentioned earlier. So I want to prove that the sum of the first n integers, positive integers, is equal to n plus 1 divided by 2. So the basis step, when n is 1, when you notice here, when n is 1, so this will be 1. So it starts from 1 to 1, that's only 1. So left-hand side is 1. The right-hand side, you get this here, and you put 1. So you have 1, 1 plus 1 is 2, divided by 2 is 1. So left-hand side is equal to right-hand side. So the basis step is good. Now let's do the inductive step. Inductive step, you suppose 1 plus 2 up to n is equal to n plus 1 over 2. I put that in blue. And then you need to prove 1 plus 2 plus 3 plus n. You add another term here. That's the Pn plus 1. You add another term. You want to prove that this is equal to n plus 1, n plus 2 over 2, which means I'm replacing n by n plus 1. This n becomes n plus 1, n plus 1, n plus 1 plus 1 is n plus 2. So that's what I need to prove. it has a left-hand side and a right-hand side. So I'm going to take the left-hand side and prove it to be equal to the right-hand side. Now you see what happened. This here is the same as this, is the same as this rectangle. So I put this one here, the left-hand side now is this rectangle or square plus this term. So I have this term right here. So once you set it up this way, it will work. Now you have to add these two. This is the same as n plus 1 over 2. This one here, you put 2 over 2 n plus 1. Now you take the n plus 1 as a common factor. You get it outside. Then inside you end up having n plus 2. So you have n plus 1 times n plus 2 divided by 2, which is exactly the right-hand side. Now let's go to the first example we introduced. 1 plus 3 plus 5 up to 2n minus 1. We want to show that that is equal to n squared for all values of n. Now basic step, when n is 1, when 1 means only have one term here. And you can find that also by putting 1 here. 2 minus 1 is 1. So from 1 to 1 is only one term. So left-hand side is 1. Right-hand side is 1 squared is 1. So they are equal. The left-hand side and the right-hand side, they are equal. Okay, now we need to put the inductive step. We suppose 1 plus 3 plus 5 plus 2n minus 1 is equal to n squared. And we need to prove this. We add another term. Now you notice here we are going by 2. So you have to add to this, you have to add 2. That's why you get 2n plus 1. You want to show that equals to n plus 1 squared. So that's what we need to show here. Again, the left-hand side is this piece, which is blue, which is equal to this, which is equal to this. So I take this and put it right here. That's your n squared. Plus, you added this term, which is this term right here. Now you add these two. Obviously, n squared plus 2n plus 1 is n plus 1 squared, which is exactly the right-hand side. I'm going to conclude with third example here. I'm going to show that 1 squared plus 2 squared plus 3 squared up to n squared is equal to n plus 1, 2n plus 1 divided by 6. So the basis step is when n is 1, that means the left-hand side here is 1, because 1 square is 1. And the right-hand side, you replace 1, 1 plus 1, 2 plus 1, 6 over 6 is 1. So you see here, the left-hand side is equal to the right-hand side. Now you set up the inductive step. You suppose this, I repeat exactly this, is equal to n plus 1 to n plus 1 over 6. And now I need to prove it for n plus 1. Now notice this one here is n plus 1 squared. It's not n squared plus 1. It's n plus 1 squared. You need to show that this is equal to n plus 1, n plus 2. You replace here n by n plus 1. You get n plus 1, n plus 2, and here you get 2n plus 3. So that's what you need to show. Again, you take the left-hand side. This is the left-hand side, composed of two pieces, this piece and this piece. So the left-hand side is composed of two pieces, this piece here and this piece here. This one is the same as this, which is this. So I take this and put it right here, see? And I take this one, put it down here. Okay, now you need to add these two terms. Now do not expand this and this, because you end up having a third-degree algebraic equation. It will be very difficult to factorize. So what you need to do is try to see if there's a common factor. So I put here 6/6 to have the same denominator here. So you have n plus 1/6. N plus 1/6 is common. From this here, you are left with n, 2n plus 1, n, 2n plus 1. From this, you are left with 6n plus 1. You do that, you do your math here, and you see that this factorized as n plus 2, 2n plus 3, and that is exactly this. And that is end of part 1. More videos to come. Thank you.